Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of movies. It's actually the MovieLens dataset, and it has 45,000 movies and 26 million ratings, and it also comes with a bunch of keywords for each movie. So the task I've decided to do, I don't know how successful we'll be, but we're going to try to predict the average rating of a movie based on the keywords for that specific movie. Now, this is this will be an interesting task for sure. Let's I started up a notebook. I have a task for today. Given data about movies and their corresponding keywords, let's try to predict the average user rating of a given movie. And we will use TensorFlow artificial neural network to make our predictions. 1 second. Okay. So the thing is, I'm not sure how much keywords are really going to convey the rating of a movie. But even if it doesn't work out, we'll still have an interesting experience doing it. So I've imported a bunch of the typical libraries: NumPy, Pandas, Plotly Express for visualization, and I'm trying this out today. TQDM basically just puts progress bars on anything you're doing, so that if you're iterating through a bunch of rows in a data frame and it's taking a long time, you can see exactly how long it's taking. Then I also have these three for pre-processing. Really, I'll get into them more later, but this is a nice function from, I think AST is abstract syntax trees, which will allow us to take. You know what? I'll just describe this stuff as I go. We have the multi-label binarizer from sklearn pre-processing, and the classic train test split function as well. For training, we'll use TensorFlow and TensorFlow add-ons, just so we can get a metric for our regression. And we'll use PCA in post-processing to get a better sense of the data and discover some interesting results. Alright, so let's get started. The movies dataset comes with a bunch of different CSVs, and I'm going to use two of them, keywords.csv and ratings.csv. Alright, so let me load those in. I'll get keywords. I'll start with ratings. Ratings.df will be the data frame for it. We're going to load it in with pandas.readcsv. I'm going to post in the ratings CSV file path. Same will go for keywords. This one will be called keywords.df. And I paste it in. Those might take a second to load up because there's 26 million ratings or something. So when that's done, I'm just going to take a look at them. Keywords.df. Okay. Alright, and here we go. So this is the one with the obscene amount of examples. Basically, we're not going to need timestamp or user ID, but what we're going to do is, right now, these are ratings given by our particular user. So what we're going to do is we're going to average all the ratings from all the users for a given movie, so that we can get the average rating for each movie, and then we're going to use that as our target to try to predict. Now, so the target isn't even actually something that's in the dataset here. We're sort of engineering it. And then in keywords data frame, we're going to basically, I wouldn't call it one hot exactly, but that's what the multi-label binarizer is going to do for us. It's going to send each one of these unique words to a new column, and with a corresponding 1 in that column, and all the other words that it doesn't have will have 0. So yeah, let's before we start, I'm just going to notice that these correspond to the same thing, right? This is a movie ID as well. So I'm just going to rename this column to movie ID so that we can perform a merge on the two data frames when we get them in the proper format. So keywords_df.columns is going to be movie ID, just so that it matches this one, and we'll keep keywords the same. Okay, so this one should have movie ID now. And now we can start pre-processing. Alright, so I'm going to start by making a word dictionary. And this is going to come in handy later. We won't have much use for it right now. But basically what that is I'm going to make a set of all the words that are found in these 46,000 movie examples. So every time we find a word that's not in the dictionary, we're just going to add it in with the corresponding code that we'll be using. So word dictionary, it's just going to be an empty dictionary. And then we're just going to iterate for word list in keywords df sub keywords. So that means for each one of these, right, it's a list of dictionaries. See? And then for each one of those, we're going to say for each word, so for each one of the actual dictionaries inside the list, so for word in word list, so for each word inside the word list, which is one of these. So we're going down these word lists. So we'll start with this one, then we'll get to this one, then we'll get to this one. But each time we're going to grab this guy, and then this guy, and so on. So for each one of those words, so for each one of these individual dictionaries here, we're going to add, we're going to update word dictionary, and the key for word dictionary here is going to be the ID for keywords. So word sub ID. Right. Because if we get the ID of a word, which is this dictionary, it'll go into ID and then return 931, right? And that's going to be equal to word sub name, which is if we go into word and go into name, we'll get the actual word. So we're saying the ID equals the name in this new word dictionary that we're making. Okay, and I'm going to try out this new feature. I mean, it's not new, but I have not used it before. TQDM, you just put it around whatever you're iterating, and it'll give you a little progress bar. I mean, okay, if you do everything right. Yes, I remember. Okay. So, this data is actually a bit interesting. If I take a look, keywords df, well, we're going to do .loc. So at index 0 and the keywords column, we're just going to get this value here. Okay. Should be a list, right? Oh. Okay. Looks like a list, but then we realize, wait, it's not a list, it's a string. It's a list that has been encoded as a string. So because it's a string, we have to turn it back into a list in order to process it. That's where this nice function, ast.literalEval, and what that does, as you can imagine, it takes a string and it changes it into a literal statement. So, for example, if I have a string that looks like 1, 2, 3 plus 4, that's a string, right? But if I call this literal eval on it, oh, let's just do it without the plus, okay? Then it'll turn it into an actual list, okay? Alright, so I'm going to literal eval each one of these. So right here, literal eval word list. Now it should work. Okay, and we get the little progress bar showing how it's working. Alright, so now we have our word dictionary. We just take a look at it. Should be pretty long. It just has all the words in our keywords in total. And let's take a look at the length of that. How many words do we have in total? Alright, wow. 19,000 words. So that presents a problem right away. That's because, well, we would have 19,000 features if we were using every one of them for prediction. Which, I don't know, it seems like too many features, and a lot of them are only going to be used once, right? So, not so useful. So maybe what we could do is just use the most common words instead. Alright, but we'll come back to the word thing. We have our dictionary now, and I want to generate the average user ratings, right? So in our ratings df, we have, again, all the a rating for a given user, and we want to combine. So for each unique movie ID, we're going to combine all the user ratings for that and take the average. So it's actually not too hard to do. Before we do that, let's actually drop these unnecessary columns, user ID and timestamp, from the ratings df. So ratings df.drop user ID and timestamp axis 1 ratings df. Alright, so now you can see we just have this nice little one. And so basically we're going to use group by and aggregate. So if you don't know what these are, they're pandas functions. Group by is incredibly useful. So if we want to group by it's called, basically it takes a column. So let's do ratings df sub movie ID. So we're going to group by movie ID. Alright, this will return a group by object. So we're going to, here, to show you what kind of contents it has, I'll just give you a little sneak peek. So for group in group by, print group. And just give 1 second. It should start printing. Alright. You can see it has separated the whole data frame into groups, starting with 1, and then 2, and then 3, where each one is the movie ID and all the ratings that go along with it. So if you had other columns, they'd show here, but we're grouping by movie ID. So it's splitting the data frame into groups where all the rows in that group are rows that have 1 for movie ID. Here it's rows that have 2 for movie ID, and so on. So if you get where we're going with this, we can now take the mean of all of these ratings. So this is where aggregate comes in. Aggregate basically allows us to affect a group, just as I described, by specifying a different function to use on each column. Now in this case, we're only applying one function to the rating column, which is mean, but we can do it like this. So if we get this here, ratings.groupby, ratingsdf.groupby movie ID dot aggregate, and we pass in a dictionary of column names to functions that are being applied. So there's only one in this case. A rating is the name of the column, and the function we'll be applying will be mean. And if we take a look at that, shouldn't take too long, but it should do exactly what I was explaining, which is add all these together, divide by the total number, and do that for each group, and then create a new example out of that. Now, why is this taking so long? Hold on. Okay, there we go. Okay, so now each movie ID has its own little thing, and we're good to go. Right? Alright, so I have to store this in ratingsdf. This will be the new ratingsdf. I'm going to take a look at it after. And I want to see, are we able to use TQDM on this? I don't know, maybe. Wait. Never mind, I don't think it's working. Okay. What? Oh no. Have I messed up my ratingsdf? Let's reload it, sorry. Okay, give me 1 second. Okay, so we have our ratingsdf now, and each one is an average rating for each unique movie, for which, interesting. I noticed that the indices are off. Oh wait, no, these are movie IDs. So it's using the movie IDs as the indices here, and that's okay. It's still considered a column in a sense. Okay, so what we're going to do now is merge the data frames. So what I'm going to do, merge, it's, if you look at pandas merge, it says merge data frame or named series objects with a database style join. So you're merging this data frame 1 with data frame 2. And you explain, you define an on value, which is the column or index level names to join on. So what that means is, okay, for our example, ratings df looks like this, and keywords df looks like this. What we're going to do, since they both have a movie ID column, is we're going to merge them. You can almost think of taking these two data frames and then connecting them across a single column that we specify. That would be the on column. And then it becomes one data frame, but the values in this are linked up to these based on whether movie ID is equal. So let's do keywords df dot merge ratings df, and we're going to specify on movie ID. So what that'll look like is this. It took this, and for each movie ID, it found the rating for that particular movie and applied it on the end. And you can see it effectively got rid of any examples where they were not matching up. So, for example, there may be ratings here for movies that had no keywords, and there may be keyword specifications for movies that had no ratings. So what that did is get rid of them all. We're left with a simple 7,668 examples. And you can see we're going to have to reduce that even more because now we have keywords, empty keyword lists. So yeah, let's save this. Let's call it train df because now we'll be working with one data frame. So this is going to be the merge. And now let's see. What can we do here? Alright, let's start by dropping these. Let's just get rid of them. So basically, if we do train df sub keywords equals, remember they're actually strings, so I can literally just type this. We'll get all the ones, yeah, let me index it at that. Oh, train df. So now these are all the examples that have this empty value. So we're going to drop all of those. So if I have dot index at the end, it'll just be the indices. And then using that, I can do train df dot drop those indices from axis 0. And now our train df should be free of any empty values. Now we're going to, okay, let's actually take the time now to convert these string lists into actual lists so that we can work with them more easily. So that's not so hard. Train df sub keywords is equal to, oh, okay, so we're not just going to turn it into a list. We're going to make it a list of these IDs. So it's a little complicated now having all these dictionaries within a list. We're going to refine that by making it just a list of the IDs for words. And remember, we have that word dictionary, so we can always look up what a specific word is. But like for example, this one we want it to become 931, 4290, whatever comes after that. So to do that, we'll apply a lambda function to the keywords column. So the lambda function is going to take in some x. Actually, let's not be ambiguous. We'll call it word list, which will be this whole thing. And that's a string, remember. And then we're going to map the word list, which is the original value, to be a new list, and we'll use list comprehension here to define it, where I'm going to define the last part, the first part last. So for in. Alright, so what we're iterating through is the original word list. Okay, and we actually have to literally val it since it's a string. So we're going through this thing, and we're going to get each word dict in it, because the elements of the list, once we've literally valed it, are going to be dictionaries. We get a word dictionary, and then what we want is the ID value from the word dictionary. So word dict sub ID. And what that'll do is just create a list of all the IDs for each word. And if we look at that, sure enough, we have what we wanted, 9314290, exactly as we wished. So now, let's just set the column equal to that. Keywords. All right. So now we have this nice train df. Here, I'll put that down here. And now we have the actual word IDs just as lists. So I think what we should do next is it's looking like a good time to split. So by split I mean let's take the rating and the keywords and make separate things out of it. So we no longer need movie ID, right? The ID itself was only helpful in linking the movies between the data frames. Now we're dealing with these word IDs and ratings. So what I'm going to do, splitting, y is going to be our train df, but so all rows and the rating column, and x is going to be train df, but all rows and the keywords column. Alright, so we'll just run that. And actually, let me name this x raw, because I'm going to do further processing on it, and I want to reference this original version of it. So x raw is going to look like this, and y is going to look like this, and the indices match up. So okay, let's see. So essentially, I want to get the words that are most common, right? Because I don't want to use all the unique words in here. It's just too many features. So we're going to use the 100 most common words. And that can be defined however you like. But we'll use the first 100. So, good way to do that. First, let's get a dictionary that maps the word counts for each word. Let's call it all words, or we'll call it word counts. And then for each word list in x raw, so for each one of these, right? For each word in word list, so for each one of these, we're calling them words even though they're really numbers, but that's okay. If a word is already in word counts, then we're going to increment it by 1. So this will be a dictionary that maps words to counts, right? And otherwise, we will set it equal to 1, because it hasn't been seen before, so we will say it's been seen once. Alright? And now, word counts looks like this. So it's not sorted, so let's sort it, okay? To sort a dictionary by value is a bit more involved than just sorting it straight up, because if we just use sorted on it, it will just give us the keys in sorted order. So what we'll do instead is we'll make this new dictionary that maps a key to a value for every key value pair in so if we take a dictionary and call items on it, it'll return tuples of the key value pairs as tuples. And that allows us to reference both the keys and the values in one setting. So we'll take this word counts dot items, and we'll sort these in the following fashion. So we'll sort it, we'll use sorted, but we'll specify that the key is going to be given by the second value in the tuple. So that's what this is saying. It's a lambda function that takes in the original tuple as item, and then returns item sub 1, which will be the value, because we want to sort by value instead of by key here. So we're sorting by value is what this means. And we also want to sort in reverse, because we want the highest values first. Alright, and so that should look like this. So why don't I just call that word count sorted. Alright, I can close this out. So at the top we have these, this one word is found quite a lot, and then the next one a little less, next one a little less, and so on. We're going to take the first 100 of these. So we can call our vocabulary, because this is really this is the feature data right here. This is if we turn the dictionary into a list, well, that will just turn the keys into a list and throw away the value data, which we don't care about anymore. Word count sorted. We make it a list and then index from the first 100. That will give us, so if we look at vocabulary, now that's just the first 100 word IDs. Alright, and that's going to be what we're going to use to determine our features. So if we look at the length of it, we have 100 words now. Okay, now back to xraw. We're going to basically go through each one of these, and this is where we'll use the multi-label binarizer. Okay, and we're going to basically give it sort of like one-hot columns, but it's like multi-hot columns. You could think of like zeros and then ones wherever we get the words that we're looking for. So we're using each unique word as a new column. So all the words in vocabulary will be our new columns. And before we start, I just want to clear out. Okay, wait, actually, hold on. Right, so what we're going to do is go through each one of these rows and rewrite this list to be just a list of the words it contains that are in vocabulary. So we're effectively throwing out any words that are not in vocabulary. So for word list in xraw, word list equals a new list. And the new list is going to be a list of words for every word in word list, but only if word is in vocabulary. It's fairly simple. One little implementational detail is we're going to have to include this here, because if we do this, it will be trying to assign by reference, and it won't actually affect the data frame. But if we do this, it's actually going right into the data frame. Like otherwise, it's making a copy. Just this thing called word list. Now it's actually the row in the data frame. Okay, so run that. Let's look at xraw again. You can see now all the words that we're not using have been removed. So now it's a list of only words that are in vocabulary. Fantastic. Okay, so you can see because we've done that, we now have some examples with empty features again. So let's just get rid of those. I'll make a set of null indices, and then for I and words, so for an index word pairs in enumerate, xraw. So xraw is a series, right? So this will give us back an index and a list in I and words. If not words, and the reason I'm using this is because if you Boolean convert a list in Python, an empty list goes to false, and a list with anything in it goes to true. So if not words means if we have an empty list, then null indices dot add I. So we're adding up all the times that we have an empty list. Okay, so 1 will go to null indices, 3 will go to null indices, and so on. So if I take a look at it, sure enough, 1, 3, and then the rest are right there. And we're going to drop null indices. So xraw is equal to xraw dot drop null indices from these axis 0. And we're going to reset the index after that so that we don't have missing indices. I specify drop true so that we don't have a duplicate index column that stores the old index data. And notice that I'm going to have to do this to the y's as well, because we need to make sure that the x's and y's are synced up. So y equals y dot drop null indices, same way. Okay, well, what happened? Did I do the wrong axis? Wait a minute. What's the matter? Why is this not working? It says not found in axis. This is strange. Okay, I found the problem. Before, when we dropped those original empty keywords data, we forgot to reset the index of that. So it's a little weird to be doing it now, but I'm just going to go ahead and reset it back here with drop equals true. So this is back with train df. And I'll just rerun this and come back. Okay, so the rows have been dropped from both xraw and y. So now we have proper, look at xraw. It's very proper. We have removed these, and we are ready to go. So this is our feature data, essentially. It hasn't been encoded yet, but this is how we'll be storing. This is all our data is right here. So this is a little weird. When I use the multi-label binarizer, I'll just show you. I'll call it MLB. It's multi-label binarizer from sklearn, and then x equals MLB dot fit transform xraw. So I'm making this new x, which is going to be the encoded version of xraw. So if I run that and then check out x, let's make it a data frame, okay? So we can see what the problem is here. Okay, so this is the proper data. You can see there's ones for a corresponding word when that word was present in the original keywords for a given example. However, we have an issue, which is we actually need those keyword IDs, right? These things. We need to know which words are which. And up here, it has been reset to 0 through 99 instead of the actual values. So what we could do is the way that this works, and the way that one-hot encoder works, and so on, is it basically goes through, and every time it finds a new unique value, it appends it on. So if we go through this and collect them in the same order, which is just, okay, 931 gets added, this gets added, this gets added, this gets added, this gets added, and then when we find something that's duplicated, we do nothing. So eventually it'll be in the order that it traversed the, so all these have been placed in the order of traversal, from the beginning to the end. And if we can go and do that ourselves to get the column names to encode this as, because we need those column names. So I'll call it word column names. And for word list in xraw, so for each one of these lists, for word in word list, so for each one of these words, if word is not in word column names, we're going to append word, right? So we'll be adding them in order, right? In the order that we see them. So if we run that, by the end, word column names should be a list of our columns. And with that, we can then, right here, columns equals word column names. So we run this, and now we have the actual word column, word IDs right there, ready to go. And what's even better is we have this dictionary that we made at the beginning. Remember, word dictionary. This is going to take an ID and give back a word that's associated with it. So what if we just apply that? So instead of making it word column names, what we can do is we can map a lambda function. So it's going to take in an x, which is, it'll take in an x, and it will return word dictionary of x. So it's just going to spit back the actual word associated with the ID. And we're going to map that to word column names. And we'll make it a list afterwards. So this will be the actual names of the words in the order we need. So let's make that word column names. Alright, run this, and now we have the actual words and whether or not a given movie has that word in the keywords. So after all of that processing, we finally have features that are going to work for us. And now we can start training. And also notice we don't have to scale the data at all, because it only takes on values of 0 and 1. So that will be perfectly fine. Training. Okay, so let's do a train test split before we start. So xtrain, xtest, ytrain, ytest. We're using train test split from sklearn to split x and y into a train and test set. And we'll specify the train size to be 70%, and we'll give it a random state. Let's do 24 today. Alright, let's take a look at the shape of x. And you can see we have 100 features, 3,600 examples. And we'll start building our model. So inputs will be our input layer, and we're using TensorFlow, so keras, tf.keras.input, and we specify the shape of our input vector, which is 100, so a vector of length 100. And we'll have two hidden layers, tf.keras.layers.dense with 64 activations, and a ReLU activation function, passing in inputs here. Then we'll do the same thing for our second hidden layer, but we're going to pass an x. And then for our outputs layer, will also be a dense layer, but we'll only have one activation. And the activation function is linear, which this linear thing really just means there's no activation function. This is going to output a numerical value with no activation function on it, passing an x. So that's because we're trying to output a rating, right? Y is our list of ratings. So we're trying to get a rating of a movie based on the keywords in that movie. So I don't know how well this is going to go, but we'll give it a try. We'll make our model, just tf.keras.model, passing in the inputs and the outputs. Then we'll compile the model. We'll use an, I misspelled it again, I always do that. Okay, we'll use an Atom optimizer. Loss function will be mean squared error. And metrics, let's see, we're probably not going to use metrics right away. We'll get an r-squared metric after we've trained. Batch size. Let's make 32, and epochs is 10. Okay, then we'll store our model's fit history in a history variable. history equals model.fit, and we're going to train on the train set. Provide a validation split of 20%. Pass in the batch size and epochs. And we're just going to turn on a callback function that is going to help us converge. Reduce learning rate on plateau. Now I wouldn't just go for this. I would see how it works without it, but I was experimenting with the data earlier and it seems like this makes it work much better. So let's run that. And so we only ran for 10 epochs, and the reason for that, as you can see, our validation loss goes down and then starts to, actually, let's run for a little longer. You can't actually see that. We'll do 100 epochs, and we'll just graph it so we can see where the lowest validation accuracy was. Sorry, loss was. Alright, so we'll make a new plotly express figure, px.line for a line chart. And the data frame we're using, well, it's not a data frame, it's a NumPy array, history.history, and it contains, actually it's a history object. Is that what this is? What's the type of this? Yeah, it's a dictionary. Okay. So, right, and the values from the dictionary we'll use is loss and val loss. Right, so it maps the name loss to an array of the losses for each epoch. And we'll do the same for val loss. And then we will give it, we'll specify the labels. So the x will become epoch, and the y will become loss. And we'll just give it a title. So, loss over time. Alright, fig.show. Alright, and we can see it's converged, mainly due to the this callback function. Here, I could get rid of it, and we'll try training again, but first let's just see. So doing this, evaluating, isn't really helping so well because we don't know what a mean squared error of 0.33 means in this context. We don't have a really good metric of understanding how well we're fitting, so I'm going to use the r-squared metric, which will sort of it sort of describes how much the data, like how far away the data is from your fit. And basically, we're going to make some predictions for that. So ypreds will be model.predict x-test. So it's making predictions based on just the x. And take a look at that. You can see we have a NumPy array of one list and individual lists, well, in between. If you look at the shape, you can see it's all one thing, but it has this extra dimension on the side. So if we look at ytest, this one is actually well, look at the shape of it. You can see that they're not the same shape. This one has this extra dimension here. And so to get rid of the extra dimension, because if we want to compare them with a metric, we need to make sure they're the same dimension. To get rid of it, we can use squeeze from NumPy. NumPy.squeeze. Now that would be this. And additionally, let's turn ytest into a NumPy array also, so that we have the same exact data form. So ytest, here, why don't I do it this way? I will grab this, put it down here. Ytest equals ytest dot to NumPy. So this won't be a panda series anymore, it will become a NumPy array. And ypreds will equal NumPy.squeeze ypreds. Alright, so right now they both look like this, sort of different. And if we look at the shapes, they're not the same. But if we apply these two transformations to them, you can see after that they will be exactly the same looking. And there's no way of really telling from this, but it looks like, these look sort of okay, right? I mean, this one's very wrong, but they don't look terrible. We're gonna get a measure of the rating based with the R-squared score. So at the top I imported TensorFlow add-ons, which is where you can find some alternative metrics. And we're going to call this one R-square. So it's TFA for TensorFlow add-ons .metrics.R-square. And then we're going to call the update state method, which is just going to basically get the values, the R-squared values for y-test and y-preds. Okay, and then we're going to print out the R-squared score. So R-squared score, and we will call R-square dot result, and then dot numpy to get the number. And you can see it is terrible. A negative R-squared value is just. But again, like, it's actually not so easy to see how bad this is. One of the problems with regression is without something to compare it to, you can't really know how good it is. Like, let's say a bunch of people were doing this, you could look at other people's results and see that yours is substantially better, especially with the loss, right? If you see that your training loss is much lower, where do we have it? Evaluate here. If this value is much lower than someone else's, you can say, okay, I'm doing better than them. But if you're the only one doing this task, you have no idea if this is good or bad. So we really don't know. And I would say, it's not great, but I mean, we were able to classify something, like something, right? So again, with these things, like, a metric is sort of a weird thing, right? So let's see if I try without the callback function, if we can get a difference in results. So this is without the callback function, and you can see the val loss is going up substantially now, because now it's going to start overfitting really hard. Oh, what? Looks like it's actually not going up too much. But if we get let's see what's the lowest. We use argmin to get the epoch with the lowest value for val loss. So if we did min, we'd get the lowest value of val loss. We get argmin, we get the x value at the lowest value of val loss. So 7. And since we're indexing at 0, we'll train for 8 epochs to try to get the best value for our model. You can see this is the lowest. It should just converge straight down. And if we evaluate this, was that a little improvement? Maybe. Maybe it was. Let's try putting this one back on for the same number of epochs. And see, this is 0.3313. And we have 335. Yeah, so that is actually better. I mean, it may be a little different every time, too. 335. Whatever. It more or less, it's performing the same. And so there's one last thing I want to do, because I don't want to just end on that note with like not knowing how our model's doing. So why don't we try post-training analysis a little bit? And this is, I think, the most interesting part of this notebook. Actually, one more thing. I want to see if I use the same training parameters that I used earlier, if we get better results. So I turn this back on. Oh wait, I never turned that back on? I meant to. I trained this for 10, and I think everything else is the same. Now I plot it, okay, evaluate, 0.337. That made it worse. I don't know what I'm doing. Okay. Yeah. So let me just. You know what? Forget it. Lose the model. Let's keep going. Post-trading analysis. So I'm going to use principal component analysis to visualize the clustering of our data. So I've described it before, and I think I'm definitely going to make a video about understanding principal component analysis. Basically, it allows us to take high dimensional data, in this case 100 dimensional, right? There's 100 dimensions here. And it's going to squash that 100 dimensional space down to 2 dimensions so that we can visualize it on a plot. So PCA is going to be PCA from sklearn, where we specify the number of components to be 2. So it's going to squash it down to 2 dimensions. And if we look at X, this is what this looks like. And I'm going to transform X using PCA.fitTransform. And I'm going to store that in a new data frame called XReduced. And the columns here, since there's now going to be 2 columns, since we're reducing the dimensionality down to 2, we'll call it PC1 and PC2. Alright, we'll just take a look at it. You can see now it has the same number of rows, but it has been squashed down to 2 dimensions, and these dimensions are the axes of greatest variance. So if you imagine a 100-dimensional space, which you can't, but there's some axis, some direction in 100-dimensional space where the data is most spread out. And so it's squashing it down along that axis. And then the second axis is going to be the axis of second most variance. So that's what PC1 is, the most variance, PC2 is second most variance. And we're going to we're basically going to plot this now on a scatter plot. So I'm going to make a Plotly express figure, px.scatter, and the data frame we're drawing from is XReduced, and the X will be the PC1 column, and the Y will be PC2 column, and we're going to, okay, that'll be enough for now, and then fig.show. Alright, so this is very interesting, right? What are these little pockets? Right now, we have no way of knowing. Somehow, the data is sort of in these clusters, and so there's some quality of this data that's causing it to separate like this in a 100-dimensional space. But also, when we squash it down, we can see it. So, let's figure that out. What I'm going to do is I want to get the word lists from before and have it show me the words that are associated with a given data point when I hover over it. And so this is pretty cool. Let's see. I'm going to make a word lists list. And that's going to be for row in xreduced.iterRows. So this is a pandas function that allows us to efficiently iterate over the rows, and basically it returns a tuple of index and the row as a series. Then we're going to append a word list into word lists. So word list is going to be word dictionary of word. So basically what I'm doing here is, sorry, I should probably look at this. X looks like this, right? Okay, I don't have to do the dictionary thing. This will just be Word. Because I already converted these to the dictionary before, I don't have to do this. Basically, this is just word for word in x.columns. So I'm making this list of all of the names of the columns if x.loc row sub 0 word comma word equals 1. So let's just dissect this. X.loc is going to locate a xy, well, not really, a row column point, right? Row sub 0, we're getting row from this iter rows thing, and sub 0 means the index. So for example, we have 0, or let's use the example 3680. Okay, let's say row sub 0 is 3680. Word is going to be each one of these, but we're only going to include this word in our new list, word list, if the index 3680 comma word is equal to 1. So you can see that's not going to happen until we get here. And here it's 1, so we'll append silent film onto word list. So word list will be, for a given row, all of the words that are present. And then at the end, we're going to append word list to word lists. It's a lot, I know. So run that, and that will take just a moment because we're iterating, but it's done. Okay. So now word lists. It's all of the words for each example, right? So what I'm going to do is I'm just going to turn it into a string. So first, I'm going to just pop this right onto the end of xreduced. So xreduced sub keywords, we're going to make a new column here, equals word lists. And then after that, xreduced sub keywords equals xreduced sub keywords dot as type string. So we just want it as a string rather than a list after we put it on. So to show you what that's doing, now we look at xreduced, we get this thing, we have the PC1, PC2, and then the keywords for that particular example. So x, y, and then keywords. We're going to specify some hover data. So this is something for Plotly Express. Hover data equals a dictionary that's going to tell us what data to display when we hover over. So for our PC1 column, we do not want to display that data. Not really important. Our PC2 column, we do not want to display that data. For our keywords column, we do. Alright, let's plot that. And now we can see the actual keywords right there. See? Fantastic. So now let's try to figure out what is causing these splits. Alright, let's look. So this is the biggest one, and I can't really see what it would be here in here. Wow, there's a lot of like gruesome words in here. If we look up here, interesting. I'm looking over here, and I'm looking over here. Well, I noticed something immediately. Well, on this side, every one of them has silent film. You see? Every one of these has silent film. Over here, there's no silent film. So it looks like PC1, which is the axis of greatest variance, is basically a split between whether or not it's a silent film or not. So examples with a high value of PC1 are most are very likely to be a silent film. In fact, it's almost guaranteed. I think every one of these is silent. And examples with a low value of PC1 are not silent film. Now, on PC2, which is this axis, it looks like I noticed that all the ones up here have martial arts. And over here, sure enough, they also have martial arts. So this looks like, okay, PC1 is a measure of how silent a film is, even though that doesn't make sense. It's high values are silent, low values are not. And PC2 is a measure of how martial arts a film is, where high values are martial arts films and low values are not. This is very interesting. I find this amazing. I guess that is what we're looking at. I think that does it for today's video. That one actually went over an hour. I think that's my longest video. I hope you liked it. If you did, make sure to subscribe and hit the bell and leave any comments in the section below. I'll see you guys tomorrow. Have a fantastic day.